So welcome to today's webinar on Rheocasting, an overview and comparison of processes. Today we will learn a lot about the challenges and maybe limitations with Rheocasting. We will see what we will learn from the experts today. The webinar today is the second one in the module called non-ferrous alloys, and the number 8 in total within the WebLearn webinar series. And you see the participant list for the registered participants on the screen now. And as you see, we have participants from all over the world, I would dare to say. Maybe there are a few places missing, but and hopefully we will get maybe not all, but almost all connected. It's quite a large bunch. The WebLearn project is a project where Jönköping University gets funding for making quick and effective competence development for the metal and polymer business within component manufacturing. And this project will ongo for 2 years, and started just before Christmas with our first webinar. So almost every other week we have a webinar on a specific topic. So since you found your way in here, do keep out on the webpage ju.se/weblearn for more upcoming webinars. And happy to see you here. Me talking is Stefan Brolin, working with external relations here at the School of Engineering. And my colleague, Ehsan Ghassemali, you will meet later on during the webinar, who's also the project manager of the WebLearn project. But the main characters of today, of course, are our presenters, Associate Professor Yesara Vanasen, from the founder and president of GISS, and also part of Prince Songkla University, which is our guest today. And we have our own from the School of Engineering, Professor Anders Jarfors, which will begin the presentation and introduce the subject in a few minutes. The format of today is just a short intro, and then we will start with a webinar and the presentation. And then towards the end, we will have a panel discussion today compared to other webinars we had earlier where we had group discussions, but this will be a panel discussion. So you have to be active and bring up questions to our experts and put them to the ball. And then late we will end in 1.5 hours, 11:30 Central European time, that is. So please, during the presentations, keep your microphones turned off so nothing unexpected happens, and do also keep your cameras turned off during the presentations. If you have questions, which I hope you have, do write them in the chat during the presentation, and we will answer those during the panel discussion. Write them either officially to everyone in the chat or to Ehsan Ghassemali. I think he is displayed as the host of this webinar that will lead the discussions. So the panel discussion are an important part today. So do give input and share ideas when we are at that stage. The webinar is recorded, so it will be available afterwards. So even if you have the camera off during the presentation, you are welcome to put it on during the panel discussions if there are openings for you to talk, since we will not record the panel discussion. So if you are unfamiliar with Zoom, you have the buttons below. Far left, you have the on and off for the microphone, and also the camera. And then a bit further to the right, you have the chat function where you open the chat and where you also can choose to address everyone, as you see in this picture, or you select ESAM in this case during this one. You're writing specifically to someone else. So by this, I will introduce Anders and hand over to Anders to start the presentation. And welcome again, everyone.
Yes, good morning, good afternoon, or good night, everyone, depending on where you are. Today we're going to talk about Rheocasting, and as Stefan said, I'm Anders Jarfors, and I will be starting this activity. So next. So first of all, we have some good news regarding semi-solid casting, because a few days ago, Per Jansson, who is the owner and CEO of Comtech, that is the manufacturer and retailer of the RheoMetal process, was appointed honorary doctor. And he's been very heavily involved with a lot of the work that we've been doing here at the university since the origination or the origin of this process, the RheoMetal process, was by Haiping Cao and Magnus Wessén at Jönköping University. So, having said that, we will talk a little bit about the semi-solid state. We will talk a little bit about thick-zone Rheo processing. Then there will be a little bit of a comparison between three leading processes. That will be GISS, SEDD, and the RheoMetal process. And then we have, of course, later on, Yesada Wanasin, who is the founder and originator of the GISS process. He will share his experience in semi-solid casting. And then, of course, the panel discussion. So next, please. The semi-solid state. Well, if you look at a phase diagram, we have a certain zone where you have coexisting solid and liquid. It's a little bit like the ice cream stage. So you start with a certain composition, and then you allow it to start to solidify. And once it comes to temperature where it starts to solidify, a certain amount of solid phase will form. And then at a certain point, everything is, of course, formed. And this is normal for every solidification process. Now, in Rheocasting, you utilize the fact that you do not have an immediate formation of all the solid phase, but you start at a certain temperature with a certain fraction of solid being formed. And most of the cast alloys are eutectic, so that means that they will display in this curve where you have the fraction solid versus temperature with what we call an E point. This point is quite important because it stabilizes the solid or the semi-solid processing. So normally, in order to have a very good semi-solid process, you need a large temperature difference between the first solid phase to form and this knee point. So that is sort of say the most critical part. Then, of course, the knee point needs to still have a certain amount of liquid phase remaining. So next, please. So turning this around, we can look at the liquid fraction versus temperature, which is sort of the inverted curve that we were just looking. So you have an area where you have your primary precipitation, and you have the knee point. Now, in a semi-solid process, you need to have a stable process window. And if you look at the slope of this curve, or take the derivative of this curve, you will end up with the green curve on the right-hand side. And you will see that there is normally quite a large range where you have a flat region, and this is normally the stable process window. And if you have a purely eutectic material or a pure metal, this window becomes very, very small, and it makes actually semi-solid processing very difficult for eutectic and for pure metals. But somewhere along the line between the eutectic and the primary phase, you have a large solidification interval, and you will have a stable region. Next, please. Now, there are discussions on various ways you can produce a semi-solid material. You can heat or you can cool it. Heating is normally referred to as Thixoprocessing processing, and cooling is normally referred to as Rheoprocessing. So depending on how your original material is being produced, this has a significant influence to what type of solid fraction you get. And if we see here, you can recognize the knee point. And if you go heating, you go by heating, you get the curved cluster to the right. And if you go by cooling, you get the curved cluster to the left. So there's quite a big difference in how the actual shape of the curve will look if you do cooling or heating. So this is very important. A few years back, we did a work where we looked at what fractions do you get on heating. And it's actually so that you get an S-shaped curve if you heat and then quench at certain temperatures. And this depends on what type of segregation pattern you have. This is also quite important in heating because depending on how high in temperature you go, you can see an evolution with time where you either have, you get a certain fraction at the melting point, and then you can have a melting sequence, or you can have at a slightly lower temperature, a resolidification sequence, depending on whether or not you are to the left or right on this S-shaped curve here to the left in the picture. And if you just in this intermediate, you sort of suffer a little bit for what you would call Le Chatelier instability, where you have a slight variation. Now, the time frame here is very important because you have to the left here a very short time. It's just going up in temperature and melting and quenching, so it's seconds, while these resolidification sequences, these are in seconds, so these are quite slow processes. So time frame of making the slurry is also very, very important. So we can take next. Once you have made your slurry, there's a purpose of having a slurry. So the first main obvious purpose we have is to increase viscosity during filling. And that means turbulence is being reduced. And that means less gas entrainment and less issues with porosity in casting, which is the main enemy of casting. Then we can use some intrinsic benefits of it. So you have shear thinning. That means that when you increase the shear rate, you actually have a more easily flowing liquid. So that means if you go from thick to thin, it will fill the thinner sections more easily. And that means also that you have a better ability to manage larger thickness variations. And with a certain amount of solid fraction, you will also change the way you distribute porosity. Now, one thing when you come to higher fraction melt is that the slurry often exhibits some kind of yield strength. And this has both positive and negative effects. One positive effect is that as you enter the die, this will add to surface tension, you could say, and it stops the filling front breakup and reduce gas entrainment even further. So it's not just a viscosity effect, it's also an effect that it enters more like a solid phase than a liquid phase. Now that also requires to have slightly larger gating systems, because if you squeeze the melt too hard, You may separate the liquid. It's like squeezing a sponge. So the liquid will leak out and that will cause segregation effects. But the main important part here is that the solid fraction actually stops sprays and splashes. Now, one thing which is important is the feeding at the end of solidification in order to actually fill and compensate for solidification shrinkage. And since the viscosity is higher, you often need a little bit larger gating, but this is also very much depending on at what solid fraction you're running it. So this is also where research comes in. If you have a solid, high solid fraction system, your feeding mechanisms are very different from normal casting. So that is something where we are trying to learn right now. So next, please. The other part is related to die wear and flow length. First of all, since you have a certain amount of solid, you remove heat outside the die, and that means that the heat load of the die is being reduced. The fact that you have solid in the melt changes the actual contact with the die. So it reduces the heat transfer coefficient. So if you have a certain heat extraction ability by the die, the gap between, or the temperature difference between the die and the melt becomes higher in order to drive that heat transfer. And that means also that the surface temperature of the die is being reduced, together with the fact that you actually have reduced turbulence. So this all affects the heat transfer to the die. Now, the shear thinning, it allows you to do better filling of sections, and it proves your ability to handle the large thickness variations. So that means it supports not only the flow length, but also the filling of thin sections. Now, very important to think about here is the flow length. Exactly how the flow length varies with the fraction solid is not fully clear because it has effects with shape and so forth of the particles. But we know that first, you will have a change of heat transfer coefficient from a very high heat transfer coefficient and a rapid heat transfer to a slightly lower heat transfer coefficient, which is H in this equation here. So if you run at the same temperature differences and you run at the same speed, you would have a flow length that would increase with your solid fraction. Exactly how this curve looks on the way up, we don't know. And where the peak is, we don't really know. But what is relatively well understood is that above 30% solid fraction, you would have a constant heat transfer coefficient. It's relatively independent. And that means that it will start to be reduced again in flow length because the heat that you carry in will be less. Okay, we can take the next. So now to the different processes. This is sort of a rationale where we have the semi-solid family process. You have fixer processes to the right, which means reheating. And there is a number of different processes. I will mention just a few. We have the Rheo processes to the left. And there is a number of processes where you see, for GISS and the SEDD process. Now, what is different with the RheoMetal process is that you actually have one portion that you reheat and partially melt. So that becomes a hybrid process. So it's somewhere in between the Rheo and the fixer process. And this makes it a little bit different compared to the fixer processes and the Rheo processes. Next, please. Now, just to show you the gist of the different processes, you have fixer forging. Here you take a workpiece, you reheat that, and you transfer that into a forging machine. This has been primarily worked with for steels because of the high temperatures involved, and you try to reduce temperatures and the heat load. Fixer casting works in the same way, where you take a billet, you reheat the billet, and then you handle it, and then you inject it in a casting die. So the process is very similar between fixer forging and fixer casting. The only difference is that in fixer casting you have slightly lower solid fraction. Now, these processes have not really gained a lot of commercial applications. There's a little bit on steel for fixer forging. Fixer casting will, well, it has problems with that you sweat and lose material during the reheating. It's also a slow process. So next, please. What actually won the fixer working side is something called fixer molding. And this is like plastic injection molding. And it's widespread for magnesium alloys. So just to give you an idea, there's about 800 machines in the world, and they produce essentially every single part you need for magnesium in Sony Walkmans, handphones, computer casings, and gaming equipment, and cameras, and so forth. And this has been the big success when it comes to semi-solid casting, and it's especially for magnesium. Next, please. Now, Rheo processing, you can have different types of processing. And of course, Rheo forging is one process that is possible, where you normally use something like a cooling slope process, where you generate the solid fraction as the melt flows along a cool plate. And then you have conditioning in a die. And then you sort of put it into the forging equipment after the conditioning. Next, please. Now, the main topic of today are the three processes: the gas-induced superheated slurry, the swirling enthalpy equilibration device, and the RheoMetal process. Now, I will not go very much into detail here, but in the GISS process, you start with a melt. You introduce a body, which you introduce gas flow into the melt, and you generate some nuclei, and then you cast it as a normal process. This process normally works at slightly lower solid fractions than the other processes, and it's not requiring as much of changes to the process as the other processes would do. Here it's gas that sort of drives the forming of the face, but it's driven from the interior of the melt. Now you can put the cooling body on the outside, and then you get the seed process. And this is a little bit like stirring your drink at the bar. You sort of just swirl the melt, and then you empty the swirling device, and then you cast like normal. The difference here is that the GISS process produces slurry in seconds, while the seed process requires minutes. So these are the main difference between these two. Next, please. Then we have the RheoMetal process, where you scoop up the metal as normal. You pour off about 5 to 7% into an EEM mold. And then you have about 6 of these cast onto a rod that are allowed to cool in a cassette. And then you take one that was cast 6 shots ago, and you dip it into the melt and rotate it, which means that you would dissolve the material that you would cast before. And then you pour it into the shot sleeve, and you create your casting. Now, the fixer element is the reheating of this part in the middle, and the Rheocasting is essentially the cooling of the melt outside. So this is sort of the difference in this process. This is also, you can see this as an internal cooling device, which is quite similar than to the GISS process, but it generates slightly higher solid fractions. Next, please. Now, if you look at it, there are a number of differences or similarities between the processes, and you will hear quite a lot more about the GISS process later on, but there are some things that we need to highlight. So one thing is wall thickness. As you will see, GISS has been working quite a lot with electronics components, and that means that wall thickness has been important. So it has a high capability of low wall thickness. Just like, as you will see, the RheoMetal process, there's a little bit of struggle with the T5 response because of the fact that you generate the solid fraction at a relatively high temperature. So you will have a low amount of solutes in the phase. You normally need to quench if you want to do T5. There's a large proven alloy capability because the GISS process is the most widely used process around the world. So therefore, there have been a lot more tries with different alloys and more use of that. Anodizing has been shown very possible. And as you will see from Jeff's presentation, there's a lot of applications, both automotive and electronics and heavy duty truck components as well. Also interesting to see that they've been worked with prosthetics and things like that. Next, please. For the SEDD process, the thin wall capability is not as dominant because they've been working mainly with high strength material. And they've been working with super performance applications. There are only 7 factories around the world that uses this process, and therefore, what type of alloys that are being used is not as high. But it works at the highest level of solid fraction that we have in these 3 processes, and also produces fairly round parts. Next, please. The RheoMetal process is intermediate in spread. It has focused on wall thickness, and I think that we set the world record with 0.35 millimeters in thickness in a radio filter. We have a moderate T5 response, just like the SEDD, like the GISS process, I mean. A moderate list of alloys, but it's been run with a fairly normal set of semi-solid materials. The dominant activities in China are electronics, but here in Sweden we have mainly automotive and heavy truck components. Also winch housings have been used. Okay, next please. Now, this may not come as a shock to you, but if you want to design for reprocessing, you essentially have the same design rules as for casting. You should try to use the same thickness everywhere. You have the same rules for thick to thin transfer. The difference is that Rheocasting will allow you to get less problems in the thick to thin transfer because you often get porosity here. Next, please. The same thing goes for ribs. You should stagger. You should reduce and restrict motion. You should not do that. You think about how the motion is made. Next, please. And you should think net shape. So you can actually very well cast holes. So you can reduce your drilling operations, and you should try to avoid using cores because cores are only adding cost. So next, please. One thing which is different is that because you have less thermal load in the dies, you will have reduced issues with ejection. And that means that you can accept the much lower draft angles using semi-solid processing. Next, please. So with that, I would like to say thank you very much and hand over to the next speaker.
Great. Thank you very much, Anders, for a very interesting introduction to the process and explanations. So it's time for our guest speaker from Thailand, just to share the slide and talk a little bit more about practical matters related to GISS process. Please, Jess.
Let me start here. Okay, can everyone see?
No, I think you have to share your slides again.
Oh.
We don't see that yet.
Okay.
Now, yes.
Okay. Thank you, Anders, for the great introduction. And I will speak on GISS technology, and we call it a superheated slurry casting. So I will give some introduction first and give the applications of the GISS technology. And this give a good introduction of the liquid as high-pressure die casting, solid like forging, and then we have semi-solid like ice cream. And what we will talk about for the GISS technology is like slurry. So it's similar to having milk or milkshake. So the brief history, we have worked on this since 2003. So it's almost 18 years. And then later in 2009, we started a company together with Mr. Flemings to commercialize this technology. And initially, we also follow the semi-solid concept. So it's just like ice cream like this. And we found in the industry, not easy to put this semi-solid into a die or into a machine or a short sleeve. So it needs a lot of modifications. So it's has a lot of limitations that we found. And later, about 15 years ago, we also work for slightly higher solid fraction, but not liquid dust. As we know, we need a freezing point like this. We also found some limitations that only some alloys that would follow this liquid solid range, and we still need some big gates. So customers were not ready to try it easily because it requires a lot of changes. For example, we found pain points in the industry that we cannot simply change the alloy for the die casters, cannot just change or modify the die casting machine, and the die sometimes not easy to modify the die because they are existing process. So we discovered that after about 6 years ago, we call it superheated slurry process to try to solve the pain points. So what it means is we have the slurry state where the temperature of the liquid is actually above the liquid dust temperature. But we have solid nuclei or the seed or the particle, whatever we call it. So this is, we call it superheated slurry state. So how is it possible? Well, let me show. Okay. So this video is a good video. The water is a boiling water. The temperature is about 100 degrees. And then we put ice in, sorry. Okay, sorry. So when we put ice in there, we can see that the temperature drops to about, let's say, 50 degrees Celsius. But we still have solid particle in there. So in thermodynamics, water at 50 degrees Celsius should be fully liquid. So this is something different from what we know for thermodynamics. And this is the reason behind that. We call it kinetic process. So it takes time for the liquid to really, to the solid to dissolve and remelt. So this is the key behind the technology of the GISS process, is that we have solid particle in sweet liquid in the kinetic process. It still takes time for the solid to remelt. So we have that metastable phase that we can cast into the die casting machine and the die, and that allow us to solve these pain points. So we have higher heat content. That's why we can fill very thin sections. We don't need to modify the die casting machine process. We don't need to modify the die design, and we can use any wide solid refraction ranges from like milk to milkshake or even for ice cream. And one of the key points is when we dealing with kinetic process, it's not thermodynamics. We can use any metals, even pure aluminum or eutectic aluminum or rod alloys can be used with this concept. So how it looks is this. You can see we start with liquid with some superheat, and then we put the GISS probe in there. And you can see here in the ladle is similar to milk. So very low solid fraction. But when it cools down, the solid fraction evolve higher and higher so that it becomes more like ice cream, or solid fraction increases to 40 or 50%. And then we have similar to semi-solid behavior. So we understand the evolution that we can start from superheated slurry, and then eventually it will evolve to semi-solid, and then evolve to solid eventually. So this is the key point. We can make any solid fraction using GISS from medium to high to low fraction, but all started from superheated slurry. And that initial solid fraction, even though it's very small, is enough to make this semi-solid behavior. And why is it possible? This is a good demonstration. The water is undercooled water. This water is minus 10 degrees Celsius, but it's still liquid. So this is like a magic that people show. With a tip of finger, it will change to solid ice very quickly. And why would that be? If you look at it clearly, you can see on the tip of his finger, he has about 1 or 2 solid particles of ice. And that is sufficient to start solidification. We call nucleation and growth. So the theory behind this is called undercooling. This water is minus 10 degrees. It has undercooling energy. It cannot change the phase because it requires some nucleation. So if we provide even a small fraction of nuclei, it will help us to overcome the undercooling energy. And then we have spontaneous nucleation and growth. So that's why only a small fraction in the superheated liquid is sufficient to have big impact. So we can make semi-solid in that way. So why, and then what would be the impacts? First, we will change the melt viscosity, we will change the mode of suffocation, and we will reduce the heat content of the melt, which will give us the benefits for high pressure die casting. For example, you can see the viscosity change when we have some solid particle in there, and that will reduce splashing and turbulent flow in the filling of the die. And this is a good video. The top one is liquid, and then we have some solid fraction in the middle and higher solid fraction. You can see that all of them can flow well, but liquid flow faster. And you can see the wave on the top. Because of the viscosity, it has more turbulent flow. But on the bottom, we can see that the wave is almost zero. So we have very smooth flowing. This is because of the viscosity. So this allows us to control the viscosity so that we have less turbulent flow up to the point of laminar flow. It depends on the Reynolds number. So normally in high pressure die casting, we cannot control viscosity. We can only control the speed. the density is constant for aluminum. The diameter of the channel is constant for a section. So the only thing high-pressure die casting can control is velocity. But with GISS, it allows us another dimension to control the viscosity so that we can manipulate the laminar flow or the turbulent flow so that we can reduce porosity in trapped air, gas porosity, for example. But another porosity that we find is shrinkage porosity. And this is because of the nature that liquid will solidify at the wall normally because of the cold surface. And then we have dendrite coming in, and then eventually we have shrinkage, network of shrinkage porosity that will give the leaks path. But for slurry that we have, we start with particle everywhere. So this particle will grow spontaneously under this cooling rate with the colder status. So you can see that we will fill all the section like this. So that allows us to reduce shrinkage porosity and then also eliminate the leak path because we change the mode of suffocation. And this shows we try to cast 6000 series in an open mold like this. For liquid, you can see a lot of shrinkage near the top up to the middle. But for GISS, we have less shrinkage for low fraction and medium fraction like this. So this proves that we can reduce shrinkage porosity. And for die casting, we have done every alloy that we can die cast. For example, ADC 12, or this is similar to A383. And we can see normally this kind of porosity at the thick section or the T junction. But with GISS, we can reduce that significantly. And this is a good demonstration. Okay, this is ADC 10. And then we hold it. Normally, this is just liquid casting. And we hold it to the temperature of the eutectic. So the eutectic temperature is about 595 for this alloy. And then we can see that at that temperature is become like eutectic. So it's not easy to flow like this. So in high pressure die casting, that's why we have shrinkage porosity. We cannot really intensify that. But this is the right video. This is GISS at 570 at the eutectic temperature. You can see that at eutectic temperature, we still have slurry stage. So intensification or applied pressure can be very transferred to the point where we have the slurry at that stage. So these, all of them give us the benefits to reduce gas porosity and shrinkage porosity. And then we have the slurry unit where we can equip with existing die casting machine like this. So we have a control unit and the probe unit. But right now, the requirement is we need a ladle system because GISS is done in a ladle. For example, like this, we start like a ladle and then we stop the ladle somewhere to allow GISS to be done in a few seconds, maybe 3, 5, 7 seconds, depending on our optimization level. And then it's like milk at this stage. We can pour it in and then we inject it in. But we need to change and optimize the process condition and die temperature. But eventually, the cycle time is faster because we have to open the die faster and the spray time is shorter. So the total cycle time is normally reduced by 15–20%. And die life increased because of the low heat content. So this is a real production for a 2,500 ton machine. For this part, it's only a few seconds of the GISS time, and then we have superheated slurry state, just like milk. And then we pour in, and then we optimize the injection. And then we get quality improvements and cost reduction. So it looks very, very simple, but the principle behind that I explained before. We have to have some solid particle in there, initially just like having milk. So what kind of benefit we can get? Well, you can imagine we can get porosity reduction from gas and shrinkage, cycle time reduction, die life extension, energy saving, and also we can use smaller machines to make big parts. So I briefly explain that, and we can discuss more in the Q&A and panel discussion. But as you can imagine, any alloys that we have done, we can optimize to have lower porosity from this, for example, like this part. And for this part, we only vary solid fractions. All the conditions are the same, and you can see different solid fraction reduce the porosity significantly. This shows the CT scan of a pressure type part. After optimization, we reduce the porosity from 0.17% to 0.06%. And also we can eliminate impregnation by this process. As I mentioned, we have to compensate for the heat content and the mold temperature, so that we need to reduce the die time and spray time, so that we can reduce the total cycle time of the process. In this case, it's about 19% for this customer. And because of the lower heat content, and everyone knows that this is one benefit of semi-solid, we have done work with customers that they can show that they have double die life. And this customer did surface analysis of the part at every 10,000 shots up to 100,000 shots. They can see almost no rough surface for GISS. And we have collected real data from customers that some customers got the life to 300,000 or 400,000 shots. Another cost saving, because slurry needs to be done near the liquid dust temperature. So the holding furnace needs to be reduced, for example, from 680 to 620, plus minus 5 degrees that we require. So customer can reduce energy about 15 to 30% for the holding furnace. Now, another important benefit for some customers is that we can reduce the tonnage of the machine. And this work was done with Bueller in Woodsville. We had a special die and special part that will have porosity somewhere in the part. That's like forced to have porosity. And then we can look at the improvements. And we did CT scan. And you can see that for 900 bars for the liquid casting, standard die casting, we get 0.4% porosity. To get similar porosity, for example, 0.3 for GISS only require 500 bars. So there are two ways to think about this. One is we can use the same pressure, 900 bars, and GISS has lower porosity. Another way is we can use lower pressure, meaning we can change to a smaller machine. So many customers did that or have done that to reduce their cost. So we've done with other alloys like silicon also. And real part has also been tried to reduce from 70 megapascal to 50 megapascal. So as I mentioned, some customer moved the die from 2,500 ton machine to 1,650 ton machine, or 1,200 to 900 ton machine. And then I will quickly go through some applications that we have done. But so far we have sold about more than 100 GISS units in 11 countries. And this is a good example for a compressor part. And they have classic problems of shrinkage porosity and leaks, and then they need to do impregnation. So customers work with us to optimize, and we reduce significantly the porosity from the thick sections, and the CT scan proved that. And also it proved that we don't need impregnation. And in this work, they did 100 sample and they found 0% rejects. And then when they go for mass production, they found that they can reduce about 70% improvement for the quality and rejects. So it's about 5,000 ppm without impregnation. Similarly, for other alloys and other parts, we got similar problems and we got similar results that we reduce porosity. Then we don't need to do impregnation or reduce the rejects after impregnation. And GISS has also been tested and worked with gravity casting, like alloy wheels like this, but I will not go into detail today. As we know, we can cast now any thin sections. So telecom parts with 0.5, 0.9 millimeter can be done. Very big parts like 1 meters have been done also. So it's similar to high-pressure die casting, but we improve it more with the superheat slurry principle. So we have also done auto parts, but I will not put all the detail on this, but all of them have similar problems of shrinkage porosity, gas porosity, leaks, impregnation, cycle time, die life. You can imagine some big parts, they have low die life and the die costs a lot. So customers want to get all the quality improvement and also the cost reduction, because the bottom line for high pressure die casting industry is the cost. Well, quality and cost, these are the two key factors anyway. So we have done also anodized parts like these examples, auto parts, EV parts. And these are just some of the pictures that we've done. And we cannot disclose many of the customers because of the confidentiality issues, as you can imagine. So this is one part that we do, because we know slurry can be applied to high pressure die casting and also to other alloys. So then we also look at other applications like 6063. So we have die casted rod alloys like 6000 series and 7000 series. These are some examples of the parts. And then we also move to, we call it slurry forging. Basically, it's like squeezing this slurry or semi-solid so we can get almost zero porosity and any alloys can be used. This is a good example of the video. So we make the slurry for a few seconds and then we pour slurry in. And then we can pressurize that. So we design our own machine, we call slurry forging machine. And it allows us to cast big parts with small tonnage. This machine has about 100 ton, or actually 60 ton tonnage. And we can cast 6000 series, 7000 series with no porosity. We did some works initially with alloy wheels like this, and then we moved to brake calipers and try the hardest and the most difficult alloy is 7000 series. And then this is the final part. It can be anodized. And then we did some CT scan 3D, and they found zero porosity in these CT scans, as shown here. We also did some mechanical testing and found about 400 megapascal to 500 megapascal and about 6 to 10% elongation and zero porosity for these alloys. We also tried these cranks with all the alloys, ADC 12 or even 8356 and then anodized. And for 6063 T6, our data shows to 60 megapascal, 15% elongation, which is similar to the ASM standard data. We also try 75 alloy with T6, and our best data is about 500 megapascal and 5% elongation. And this work is still ongoing. And finally, I want to show that because slurry has lower heat content and can fill anything, we have casted a slurry of aluminum and other alloys with wood. and wood doesn't burn and can fill very thin sections like this. So the summary of this is we are positioning ourselves that we are here. We improve quality of die casting and also try to reduce the cost at the same time. This is because from what we found in the current mass production requirements, the two factors that are most important for customers are cost and quality. So we are trying to apply GISS to give both of these factors, which is reduction of production cost and also improvement of the quality. So I will stop here because I think it's better to have some discussion or questions. So thank you very much.